Sounds like metal. This is going to be a loud one today. We've got these big machines running behind us, so we'll be talking all about this machine and how it makes composite parts, actual carbon fiber parts, in a 3D printing style process.
Hi, my name is Devin Young. I'm the lead engineer for an organization called UMAMI, which is the Utah Advanced Materials Manufacturing Initiative. And for the past 2 years, I've been lead engineer in this project. We're trying to demonstrate using this machine over here, which is called the Impossible Objects Composite-Based Additive Manufacturing, or CBAM for short, printer, to demonstrate its use for low-cost sustainment for legacy aircraft in the Air Force. So essentially what we're trying to do is find these parts that they're running into supply chain issues, these legacy aircraft that they're running out of parts for. So they're 30, 40 years old, the original parts are failing, they don't have the original tooling. So we're trying to demonstrate that this CBAM technology is a viable alternative, a low-cost strategy for producing replacement parts. So that's essentially what I've been working on, and so now we're working with ElectraFly as a kind of way to demonstrate that the technology is useful to kind of lower the weight of their prototype machines.
We'll go through the entire process and we'll talk about how CBAM works, what does it actually mean, and then we'll also talk about when is it applicable, when is it the best solution. Obviously you've got traditional composite layups and you have milling, so you could mill like composite billets, or you could mill aluminum or other metals, or you could just go with 3D printing. And so we'll talk about where exactly the CBAM technology fits on that scale and when it would be appropriate for your use, and why ElectraFly is going to use CBAM technology for some of our parts.
So these are bitmap images that it's going to use as the templates for what it's going to print on each sheet. So it's going to print the cross-sectional shape of the parts for each layer.
Okay, so you just handed me these parts here. So these are made out of PEEK?
Yeah, that's a PEEK matrix with carbon fiber reinforcement.
Okay.
It prints on here. I'll show you.
Okay. They sound almost like metal when they're when you tap them together, and they're very stiff. Now, would I be able to break these if I tried?
I don't know. I haven't dealt much with that. Probably, maybe, but I'm not sure actually.
I mean, I'm putting a pretty
it
good.
Probably depends what you do to them.
I'm putting a pretty good squeeze on some of these parts, and it's zero flex.
This is one of the reinforcement sheets. It's randomly oriented carbon fibers. About 1 inch is the average length. So I'm not sure if you can see the fibers in there. But yeah, so it's going to print on each one of these sheets some images, and then it's going to deposit thermoplastic powder on top of that. You stack them all up, compress them, and heat them together, and then you're going to get solid parts. Here's a stack of blank sheets. Here's a stack of printed sheets.
Oh, so
this is what it's like when you've got the actual thermoplastic powder on it.
So those have actually been printed?
Yes, these are ones I keep around just for demonstration. I'm not going to ever make these out of parts, and it's getting all smudged, so I'll have to throw this page away.
The smudge, it's almost like a powder. A powder's been applied to it, and you can move it with your fingers.
Yeah, if you touch it. So once it's been deposited, you don't want to play with it.
Right.
You want to disturb it as little as possible before you get it heated and compressed.
Those sheets then get heated and pressed. That's the final product.
So you're going to end up with something like this. This was 60 sheets worth. So now it's about this thick. It's about, this is a little over 3 millimeters, I think. And so you've got these areas where you can see the parts that we put in here. There's a bunch of tensile coupons. And then you can see on the sides where there's no parts, this is unconsolidated material. So this is what you have to remove.
So this is basically like, if we were to equate this to an FDM style print, then this would be the support material.
Yeah, in a sense though. It's the support material, but it also forms the reinforcement for your parts itself.
These are loose, like we could just
this is what we want to get rid of. So this stuff here where it's loose on the edges is loose. We're going to remove that. Like we'll cut the big parts off with a knife or something, and then we'll sandblast the rest away around the actual parts. So that kind of ends up looking like this.
This is the unconsolidated material.
Yep.
And this is the pressed material.
Exactly. So this is going to stand up under the media blaster. This is going to move exactly. So this is where the powder was. This is where there was no powder.
Yeah.
So it's just going to stay unconsolidated.
This is really interesting to actually look inside the geometry of the part there,
Yeah.
where this part has not been removed, and you say it's sandblasting that's pulling that out.
Yep. Yeah.
Wow.
So there you go. This is sort of this is what a final part will look like with nothing on it.
What's this part used for?
It's just a demonstration piece. It's a scaled down version of a part for an aircraft.
How does CBAM, how does this process work in areas like this? To me, it looks like this was oriented
Yep.
sideways here. So obviously you have your layers going this way. How do you press those areas?
That's going to be support, like you were saying, that's the support material in FDM. The unconsolidated fibers where nothing's been printed, that's going to serve as your support material. It's going to
So the unconsolidated fibers, they will handle the compression.
Yep.
But then you can just pull them away because there's nothing bonding them together.
Yep, exactly. So you don't need support material the way you do in FDM. You might put pillars around if it's a big enough part to keep it from delaminating. Once you pull it out of the press, you get relaxation forces. But they're never attached to the part itself. So that's kind of nice. You don't have to worry about removing them and having a weird surface finish there when you remove them.
Well, you say that there's not support material, but in a way it's almost like the entire thing is support material, right?
Yeah, that's true. It's just not support material in the way we think about it with FDM. It's the unconsolidated material serves as the support material, so you don't have to think about where your support's going to be, or even think about what type of overhangs you're going to need to support.
So this whole entire stack will go into the press.
Yep.
And whatever's not used is garbage, and so you either use it or you lose it.
Exactly. So when we're designing these builds, we're going to try to maximize how much work volume we're using there. So that's why we try to put multiple parts in the builds. You try to use as much space as you can. That way you're minimizing your waste. Okay, so now we're just going to see how it goes. It's going to punch index holes in the corners so it can stay on the pins. That way the images don't get all
shuffled.
Yeah, exactly.
Or maybe misaligned, I guess would be.
That's a better word.
Oh, so it actually did print something on it. It's not just a test.
Yeah, you don't really see it when it's coming through.
So you have your stack of sheets.
Yep.
And then those come onto this other conveyor belt, and this is where they're printed, is that right?
That's right. Yep.
Okay, and what's going on between the two conveyor belts? It's the machine on top of that.
That's the powder trough shaker. So it's going to, when it moves underneath between that gap, a sensor is going to trigger and shake powder down onto the sheets.
Okay, so this is more of like a gluing area then, or?
Yeah, so this is deposits of wetting fluid. Just so the powder will stick to the sheet. Yeah, and then it's going to only stick to the wetting fluid once it goes into the powder trough.
Okay, so if we were, right now you've got the machine paused, but if we were to see this in action, these sheets would be going forward and they would still look like blank sheets as they go into the powdering area.
Yeah, so you can go ahead and watch. You can very lightly, if you're at the right angle, make out the wetting fluid. You can see kind of the outline. It's hard to do. Here, I'll open this, come over here. You might be able to see it. No, I can't see any of it.
Well, I mean, you can see that maybe there's something there, you know?
Yeah,
like,
sometimes you can see it.
So we worked with Dr. Dorinda Larson about trying to use CBAM technology for ElectraFly. Why is that a good fit? Why are we here?
You're using aluminum for these parts here, and which is a great material. Problem is it's heavy for what your uses are. So you're trying to get the weight of the part down. The FDM parts you try to print are too weak for your purposes. And so here you're getting kind of an in-between here where you're going to get better strength actually along the length of your parts because of the carbon fiber reinforcement, but it's going to be lighter than the aluminum. So I think that's how we're definitely going to be able to help you out.
And a lot of the parts at ElectraFly have complex geometry.
Right.
And it's not as if we could take those parts and like lay them up on traditional layup methods of composite. It's not doable. With the CBAM technology, we can get a composite part with geometry that is not really possible in another way. I mean, certainly there's things like, you know, molds and that kind of stuff, but even that couldn't fit the complex geometry of what we're doing here.
Yeah, it's just the amount of effort you'd have to put into it to achieve the same geometry with like a traditional manufacturing method would probably be way too cost prohibitive to achieve.
Are you pressing that now?
Yeah.
So now the big press is coming down there. So you don't actually press it all at once. You actually have a pressing schedule.
It goes in stages, yeah. It's a recipe. I print it kind of the ways, you know, because usually you print one of those at a time, an FDM machine. So I print the entire quadcopter in one build. So I did it all at once. So, and I'd like to make it though as compared to, you know, because it'd probably give a lot more, you know, it's going to be a lot stiffer than, I think the guy I watched, he usually prints out all sorts of stuff. I think the main one he uses and flies around is made out of polycarbonate.
Is this one nylon?
Nylon, yep.
Okay. So this is a nylon binder on a carbon fiber sheet.
Reinforcement, yep.
Yeah. Okay.
Yeah.
You know, so we haven't talked about the last stage in great detail, which is the sandblaster.
Yeah.
I'm wondering, I was just taking a look at this, wondering if we can come over here and take a second look. So, one of the things that I thought was interesting, I'm looking at your parts over here by the sandblaster that have come out of the CBAM machine, and to me, that looks almost exactly like a fossil. You know, I can see what your part is here, and I can see that you're breaking away the rest of it.
That's how it feels, actually. I tend to refer to this part as extraction for that very reason. It's like extracting fossils. So, in a sense, it can be kind of fun. Depends how much I got to dig through, though.
How long is it going to take you to dig through that?
Well, it depends on what I'm doing, though. Because if I can get in these little guys, these are little mosaic tile pieces I printed off here. And they're about, quarter inch thick, though. So it's not going to take too long.
And this stuff, it machines, it sands,
It's pretty much like machining and sanding nylon.
Okay, nylon.
Yeah. So,
Really?
yeah, it machines really well, really easily. It's probably not exactly, I don't know how to quantify machining. It's probably wearing out your tools a little more quickly than just nylon would.
Right, it's a little more abrasive with all the carbon fiber in it.
Yeah, exactly. Yeah. But it doesn't feel like you're doing anything, but it's pretty easy to do. I've done a fair amount of it where I've cut it with band saws, I've sanded it down, I've drilled it out, and it all works pretty easily. So.
Okay. Wow, can we see you do it?
Oh yeah, sure. I can drill some of these out right now. Should probably plug the guy in first.
Engineer's first mistake.
Yep. So just to demonstrate, it's really easy to machine.
Yeah, it does. It looks like nylon the way it chips out.
Yeah, it really does. And so it's, yeah, as far as post-processing like that, it sands really well, machines well.
Okay, so the whole process then, starting back here with the CBAM machine, then we print it, we stack it, and then we take it to the press where it's heated and pressed, and then we bring it here to the final station where the parts are sandblasted and removed from the support material. And this is the final step in the process. Did I miss anything there, Devin?
I don't think so.
Getting all suited up for this?
Yeah.
Are you checking out a cow for colon cancer?
Kinda. No, it just there's lots of little carbon fibers in there. It gets super itchy if I don't use it though, but it was amusing that this is the solution I found to that. Okay, so this is the extraction step. So this is some leftover piece of one of my build blocks. It's still got some little demonstration parts in here that I didn't really need for anything specific. So I kind of left them in there. Haven't gotten around to extracting them yet though. So we're going to use the media blaster to remove some of this material around the outside edge so we can start excavating these parts so we can get them out of the build block. Alright, so here we go. Remove some of this material. Try to extract this little lizard here.
What kind of media are you using?
It's glass and silica.
Glass and silica.
Yeah. And we keep the air pressure low enough that as long as you're not hovering on one spot for a really long time, it doesn't seem to wear away the actual consolidated material. So it's just going to remove the unconsolidated fibers and then keep the rest of the part intact.
So after sandblasting, we'll have a finished part, right?
Pretty much, yeah. It should be good to go. So there we go. There's our little lizard.
All right.
No fibers on the edges there. As far as I can see. Yeah. Little lizard guy. It's a mosaic.
Obviously, there's a lot of X and Y geometry to that.
Uh-huh.
And if you start going more geometry with overhangs, and that's not a problem.
Not really.
Okay.
Might make it a little more hard to extract the fibers from under the overhangs, but not in general. It's usually pretty easy.
So as long as there's no cavities in the material,
yeah.
The CBAM technology is, or the CBAM, what would you say, technology process, the CBAM process works?
CBAM, yeah. I say technology or process, either one works.
Okay,
yeah.
Well, awesome.
But even then, there might be some applications where maybe it doesn't matter if it's filled with material, so
it's still the
might actually end up making it a little lighter.
That's what I was just going to say, is the unconsolidated material is going to be not heavy, right?
Yeah, exactly. It's pretty light. Stuff comes out to about 1 gram per cubic centimeter is the weight, or the density.
1 gram per cubic centimeter.
Yeah. It's about half what alumina is, I believe. I think alumina is about twice that.
So let's go check out the strength numbers.
Yeah. So right, so I did some mechanical testing of dog bones, and what I came up with was, I tested 52 dog bones total. These are all the different batches I tested. They have different numbers in each batch. Ultimate tensile strength, for metric, was about 83.6 megapascals, 18.2 standard deviation, 1.37 gigapascals for ultimate for modulus, about 0.132. Oh wait, no, I'm mixing my numbers up. 9.45 gigapascals is the modulus, about 0.91 is the standard deviation there. And that's supposed to, so again, ultimate tensile strength average about 83.6, whereas for aluminum that's about 310 megapascals. And then stiffness, the modulus was, what did I say? 9.45 gigapascals for CBAM material. This is a PA12 with carbon fiber reinforcement. And when I looked up for aluminum 6061, 68.9. So
is it safe to say then that we're about a third of the strength?
Yeah, third of the strength.
And so we're about a third of the strength, and that's per gram, right? So like for 1 gram of aluminum, the strength would be, I guess I'm not, you know, this is where it shows that I'm not an engineer, but the strength for aluminum for comparable weight.
This is just, for comparable weight, we'd have to do that calculation. This is just the
this is
as measured
per dog bone.
Strength. Yeah.
Okay, yeah. So the little testing, the dog bones, the little testing pieces, those are going to be substantially lighter weight.
Yeah.
Than an aluminum counterpart, right?
Yeah.
So
I think they'll end up being about half the weight, I think.
The reality is that these numbers are showing that it's like a third of the strength of aluminum, but the reality is that if we were to use it on a weight by weight basis, like so if we use 10 grams of aluminum to make a dog bone and 10 grams of the consolidated peak, we would be more on par, strength to strength, right?
Yeah. Yeah, you're probably still going to get better performance depending on what you're doing with the aluminum though, but that goes back to, there might be other considerations, you know.
And this was not tested in peak, this was tested in...
This is a PA12, so we expect the peak matrix you're going to have better performance. Right. Stronger. I don't know what that is. This is stuff I've been able to do for my project specifically, so I know these numbers. I don't know what it is for peak quite yet. I'll actually be doing that for part of my PhD though, so I'll have some numbers of that in a while, but for now, don't have it.
Yeah, okay. Yeah. Well, that makes sense. Yeah. And do we have any carbon fiber numbers or like a standard traditional layup?
We have to look it up.
And again, you know, we're looking at all this stuff through the eyes of ElectraFly. Our purpose is to build this flying machine, so weight is super important. And to get the complex geometries, it all comes back to the idea of getting complex geometries in a composite part. So our alternative would be to machining these parts. So the CBAM technology is really for these really complex composite parts without any special tooling, because it conforms more to the 3D printing style process where there's no tooling required. Is that all about right?
It sounded right. I was kind of looking at the computer, so I may have missed it, but the parts I heard sounded good to me.
Okay.
Yeah, see, if we're going to compare, IM7 855 is what I'm used to, what I've dealt with mostly at school. I don't think this is 885, but let's see. Here's some Hexels, IM7 hex toe carbon fiber. Let's see, what do they got for tensile strength? Oh yeah, 5,654 for the 12K, about 5,500 megapascals, so it's definitely well below that. You know, 2 orders of magnitude below actual carbon fiber though. But you don't have the issues of doing the layup process. You can create geometries with this stuff you can't create with that.
Right, so So the reality is, like, if you had like just a straight up unlimited budget or something like that, then yeah, you go and you lay it up in carbon fiber. That's carbon fiber's still king. Is that fair?
If you just need pure strength, but there might be some things you can't really do that layup with. You can't make that part out.
Right, and it obviously it would be like totally disregarding costs.
Yeah.
Because that would cost a fortune relative to what we're able to do here. So like if we're looking at like a straight up 3D printed part, this is a great alternative to a 3D printed part. So we're getting strength that's higher than what we would see in 3D printing type processes, but we're not. It's kind of like an in between, like a 3D printed part and a milled aluminum part or a carbon fiber layup. You know, so if you wanted the gold standard, you're going to pay a fortune and you're going to get a carbon fiber layup. In which case, you might not be able to do that just because of it, depending on how complicated your geometry is.
Right.
And okay, so on the spectrum, if we're on one side of the spectrum we have 3D printing, and on the other side of the spectrum we have insane carbon fiber layups, followed by machined aluminum, then the CBAM technology would be kind of in between the machined aluminum and the 3D printed part in terms of strength and cost and all that.
Right, yeah. There's a lot of different performance metrics to check there, because you can probably get some, with the FDM stuff, with the continuous fiber toes, you can get some really strong, really stiff parts, right? But then you got the time cost, and then you're going to have worse interlayer properties than you'd expect to go with CBAM. So if that's a consideration, CBAM let me go for it. So really ends up just being specific to whatever your application is.
Right, and ElectraFly, you know, our machines, we definitely have budgetary restrictions, and and we have very complicated geometry, so that makes this CBAM technology a really good fit for us. And I guess this is kind of like video number 2. Last time we introduced it, this is more of an explanation of the process. So video number 3 in this series should be more about like maybe test it until we break it, kind of see it on the application. Does that sound good to you?
Yeah, I'm probably getting those tolerances, see how it turns out. You know?
Awesome. Alrighty. Anything else we missed?
I don't think so.
So there's 2 CBAM machines west of the Mississippi, and this is what we call a beta.
This is the Pilot 1 machine. So the other one's at NIAR in Wichita. They've got one, but they've got the Pilot 2, which is the first production one, I believe. So it's an upgraded version of this, so they've modified a whole bunch of things. A lot of they've included a lot of things, in my understanding. I've never seen one myself, but I'd like to. But and then I know there's another company who's got 2 somewhere, and then I think the rest of them are at Adam Possible Optics headquarters. There's probably around 10 or 11.
10 or 11 machines total.
Might be more. I couldn't say. That's my understanding.
So Impossible Objects, they have a bigger build volume machine, right?
They do, yeah. This one was upgradable to be a bigger volume, so you can 12 by 12 units this size instead of the smaller one. We should never get it on this machine. We already had all the materials, so we weren't going to bother upgrading to the higher volume for this one at least. So.
Yeah, and now Impossible Objects, the reason that the machine is here is because they have partnered with UAMI. Is that
right? So UAMI is doing this project as part of America Makes Maturation of Advanced Materials for Advanced Manufacturing for Low-Cost Sustainment, or MAMLS, M-A-M-L-S, MAMLS, they call it though. And so UAMI has awarded a grant to demonstrate this technology, to be able to use it demonstrate it essentially for low-cost sustainment for the Air Force.
So you're just validating what can be done and the utility of this from the Air Force's perspective.
Yep.
Did I get that right?
Yeah, that's about exactly it. You said it better than I did, so yeah, it's perfect.